In this video, we're going to talk about a fifth factor which affects the acidity of molecules, and this is going to be about electron withdrawing groups, how electron withdrawing groups, or what we might sometimes call inductive effects, affect acidity. So way back, I think we talked about the acidity of HF versus CH4, and we said that if we were to, say, dissociate a proton from this and give F minus and H plus and CH3 minus with a lone pair, we said that fluoride ion is much more stable than CH3 minus. This is very unstable here. CH3 minus. And why would we say that was? Well, it was because of electronegativity. The key factor here was that fluorine has an electronegativity of 4.0 and carbon has an electronegativity of 2.5. And that helped to explain this 10 to the power of 50 difference in acidity between HF and methane. Now, we can't actually change the acidity or the electronegativity of carbon. But what happens when we replace H with other groups? We can't change the electronegativity of carbon. What we can change is the things that it's attached to. Question mark. So, for example, if we're looking at CH3 here on one side, lone pair, negative charge, what would happen if we were to, let's draw the lone pair on the other side. Say we imagine we had, instead of 3 hydrogens attached to a carbon, we had 3 fluorines. So in this case, what would happen? Well, we have a very electronegative fluorine atom attached to a carbon. These fluorine atoms would pull electrons away from the carbon, such that our fluorine would be sort of delta minus, and we would start taking electrons away from our carbon. This would have the effect of, it's effectively more electronegative. I mean, the carbon still has an electronegativity of 2.5. That hasn't changed, but it's fluorines that are attached to it have the effect of almost making it more effectively electronegative. So that's also going to stabilize the negative charge. So this is going to become more stable. And you can imagine that as we increase or decrease the number of fluorines, this is going to have an effect on the stability as well. So as we go from monofluoride to difluoride to trifluoride, then we're going to become more and more stable as we increase the number of fluorines that are attached. That's not really very well spaced now, is it? So let's draw the fluorine, hydrogen, lone pair, negative charge. So again, this is more stable on the left, and this is less stable. Okay. So what does that mean for acidity? So stability, we can draw a little greater sign. So the more electronegative groups we have attached to our carbon, the more stable it's going to be. So what does that mean for acidity and basicity? Well, you can imagine that if we have, so F3CH going to F3C minus plus H plus, or F2C, actually HF2CH going to HF2C minus plus H plus, and we're basically going to increase the number of hydrogens and decrease the number of fluorines as we go. So H2FC minus plus H plus, and then we'll have CH3H going to H3C minus plus H plus. So we said that this CF3 was going to be the most stable, and this is going to, CH3 minus is going to be the least stable. What was that going to mean in terms of these dissociation constants? Well, this is going to mean that this is going to be the most favorable reaction because we're going to get the most stable conjugate base. So this is that's going to mean that this is the strongest acid, right? So the more it can dissociate, the stronger the acid. So stronger acid, and this is going to be the weaker acid. So the bottom line here is that the more electron withdrawing groups we're adding to a given atom, the more we're going to make it progressively more and more acidic. And this doesn't just apply to alkanes. This can also apply to, one more example, it can also apply to other types of species. So if we have a carboxylic acid, for example, 2 carboxylic acids, so this acid and this acid, here, if we draw all these things out, all the fluorines out, we'd see that there's also an inductive effect. Inductive meaning that it's inducing a negative charge. It's actually helping to induce a positive charge on this carbon here, and it's pulling electrons away, and that means that this is going to become a much more stable conjugate base than it would be in the absence of these fluoride ions. So O minus, so CF3. So this is going to be more stable, and then H3C O minus, this is going to be less stable, which means that this is more acidic and this is less acidic. And as it turns out, there's a factor of about 10 to the 5 difference in acidity between these two species, trifluoroacetic acid and acetic acid. So again, bottom line for this video is just that if we have neighboring electron withdrawing groups, these are going to help to stabilize the negative charge of the conjugate base, and therefore it's going to make our conjugate acid more acidic.